Welcome to The Explainer. Today we're diving into a literal mindbender. We're going to trace the historical evolution of quantum physics. And honestly, this isn't just about complex math or dry historical dates. It's about a fundamental, ground-up shift in how human beings understand the universe.
To really get into the weeds, we're grounding our explainer in an incredible piece of source material, the Arabic translation of Werner Heisenberg's Physics and Philosophy. Heisenberg wasn't just sitting on the sidelines observing the quantum revolution. He was literally one of its chief architects. Through his writings, we're getting a direct, front-row seat to the intellectual earthquakes that completely rocked the scientific world in the 1920s and 30s.
So before we get into the history, I want to ask you something. What if the world you see isn't actually there until you look at it? Just sit with that for a second. In classical physics, a billiard ball rolling across the table has a definite position and speed, whether you're watching it or not, right? But as we're going to see, the pioneers of quantum theory discovered that at the atomic level, objective reality as we know it completely dissolves.
Okay, let's dive into this. Here's our roadmap. We're going to start with the birth of quanta, then cover the atomic revolution, wave-particle duality, the new quantum mechanics, the uncertainty principle, and finally, wrap it all up with the Copenhagen Interpretation.
Section 1. The birth of quanta. Breaking classical physics. Picture it. It's the late 19th century. Physicists are feeling pretty confident. They felt they had a rock-solid grip on the universe, using Newton's mechanics and Maxwell's theories of electromagnetism. But there was a glaring issue. Classical physics completely and utterly failed to explain thermal radiation, basically how heated objects emit light. And because of this one crack, the entire classical foundation crumbled incredibly fast. In just 24 years, a rapid-fire succession of discoveries turned science completely upside down. It kicked off in 1900 with Max Planck, accelerated with Albert Einstein in 1905, was applied to atoms by Niels Bohr in 1913, and culminated in a massive paradox thanks to Louis de Broglie in 1924.
To really grasp this timeline, we've got to define the concept that started the whole avalanche: quanta. Basically, these are distinct, indivisible packets or bursts of energy. Back in the summer of 1900, Max Planck realized the only way to mathematically solve the thermal radiation problem was to assume energy doesn't flow in a continuous, smooth wave like water, but rather in distinct, choppy bursts. Heisenberg actually recounts this famous anecdote where Planck was taking a walk in the Grunewald forest with his son, and he confided that he felt he had just made a discovery of the first order, maybe the biggest thing since Newton. And he was right. By 1905, Einstein took this a step further, proving that light itself actually travels in these discrete packets. That completely changed the rules of the game.
Moving to Section 2, Revolutionizing the Atom, Rutherford and Bohr.
And this brilliantly illustrates how the scientific community pivoted. Once they proved light behaves in these strange quantum packets, physicists shifted their focus to the very structure of matter itself. In 1911, Ernest Rutherford figured out that atoms have a dense, central nucleus with electrons orbiting it, kind of like a tiny solar system. But there was a catch. Classically, this model made zero sense. According to the old rules, orbiting electrons should lose energy and just crash straight into the nucleus. So, in 1913, Niels Bohr swoops in and rescues Rutherford's model. He proposed that electrons are forced to obey quantum rules. They exist only in distinct, fixed, stationary states. They don't crash, they just instantly jump from one fixed orbit to another. This is huge because it finally explained the incredible chemical stability of elements. A carbon atom stays a carbon atom purely because of these rigid quantum rules.
Section 3. Wave-particle duality, the great paradox.
Now, what's really interesting about this slide is the sheer cognitive dissonance it represents. By the 1920s, the physics community was tearing its hair out. The experimental results were pointing to a total, unexplainable contradiction. On one side, you have particles. They're point-like, they have a definite position and momentum, and they act like tiny billiard balls. But on the other side, you have waves. They're spread out over a large space, characterized by frequency, and they interfere with one another. Then, in 1924, Louis de Broglie drops a bomb. He proposed that not only does light act like both, but matter itself, stuff like electrons, also exhibits this dual behavior. I mean, think about that paradox. How on earth could an electron be a concentrated point of matter and a spread-out wave at the exact same time?
Which brings us to Section 4, the new quantum mechanics, a mathematical resolution. The physicists desperately needed a way out of this paradox. They realized it was time to stop relying on pictures in their heads and just trust the math.
And the breakthrough came in a rapid 1-2 punch. In 1925, Heisenberg invented matrix mechanics, which was a purely mathematical system that threw the whole idea of physical electron orbits right out the window. Just a year later, Erwin Schrödinger developed wave mechanics, and shortly after that, Max Born introduced the crazy idea that these weren't physical waves of matter we were dealing with, but probability waves. The kicker? Schrödinger's and Heisenberg's models were proven to be mathematically equivalent. They were literally two different languages describing the exact same truth. But don't miss the massive philosophical shift here. The math was no longer describing definitive paths. It now relied purely on statistical probabilities.
Section 5. The uncertainty principle. The limits of knowledge. So, the crucial point is how this reliance on probability leads us directly to the most famous limitation in all of physics, the uncertainty principle. Formulated by Heisenberg, it dictates the fundamental inability to simultaneously know both the exact position and the exact momentum of a quantum particle. Basically, if you measure the position of an electron with extreme precision, you completely lose all knowledge of its momentum, and vice versa. And it is absolutely crucial to understand this next part. This is not a flaw in our measuring tools. It's not human error. It is an inherent blurriness built into nature itself. The particle simply does not possess a definite position and momentum at the same time.
Let's walk through Heisenberg's famous thought experiment step by step to prove why this happens. Step 1. Imagine trying to observe a single electron using a super high-resolution gamma-ray microscope. To see the exact position of the electron, you need to hit it with a very short wavelength of light, like a gamma ray. Step 2. That high-energy gamma-ray photon physically strikes the electron, so it can bounce back into your microscope lens. Step 3. That very impact violently alters the electron's momentum in a completely unpredictable way. So by the time you've measured it, it's already gone. The very act of measuring the position permanently destroys our knowledge of its momentum.
Now, as you might guess, this statistical, unpredictable reality deeply troubled a lot of scientists. Albert Einstein famously declared, "God does not play dice." Einstein heavily favored a deterministic world. He strongly believed there just had to be deeper, hidden variables we simply couldn't see yet, and he fiercely rejected the idea of inherent randomness. Heisenberg, on the other hand, argued that this unpredictability was a fundamental, unavoidable trait of the universe. It was an intense, profound clash between classical certainty and quantum probability.
And that leads to Section 6, the Copenhagen Interpretation, Philosophy of the Quantum.
Let's move to the Copenhagen Interpretation and see how this builds into the ultimate philosophical conclusion. Working together in Copenhagen, Niels Bohr and Werner Heisenberg synthesized all this math into a cohesive philosophy. The cornerstone of their interpretation is complementarity. Bohr argued that wave and particle behaviors are mutually exclusive, but they are equally necessary to understand the whole picture. You can't see both at once. Crucially, it is the observer's choice of experiment that decides which face the quantum system reveals. Set up a wave experiment, it acts like a wave. Set up a particle experiment, it acts like a particle. The language of classical physics completely fails us here. The system genuinely does not have an objective reality independent of our measurement.
Which brings us right back to our opening thought. If the act of observation, the physical interaction with a measuring device, essentially forces reality to snap into a definitive state at the quantum level, what does that mean for the universe when no one is looking? Einstein's writings show us that science doesn't just quietly discover nature, it actively interacts with it. We're not just spectators, we are active actors in the great drama of existence. I hope this explainer has left you as completely fascinated by the history of the quantum world as I am. There is just so much more to learn. Thanks for joining me today, and keep questioning the reality around you.
Does the electron truly exist before we observe it? Just pause and think about that for a second. You know, we walk through our lives assuming the world around us is solidly, fundamentally real, right? Whether we're looking at it or not. But what if the very fabric of the universe actually behaves entirely differently? What if the literal building blocks of reality are just ghostly possibilities until the exact moment you measure them?
Welcome to this explainer. Today, we're exploring one of the absolute most mind-bending intellectual revolutions in human history. We're diving into Werner Heisenberg's physics and philosophy, specifically focusing on Chapter 3, the Copenhagen Interpretation of quantum theory. Honestly, this is the framework that didn't just change physics, it fundamentally rewired what we consider reality to be. Okay, let's dive into this. To make sense of it all, we're going to follow a clear 5-step path. First up, the quantum shock. Second, Heisenberg's uncertainty. Third, the classical language paradox. Fourth, probability and the possible. And finally, observation creates reality.
So, let's jump right into Chapter 1, the quantum shock.
Back in the 1920s, physicists had this really dramatic realization. They figured out that the microscopic realm completely defies the rules of the visible universe. I mean, think about the classical world of Newton and Einstein. It's a predictable, objective reality, a place where, as Einstein famously put it, God does not play dice. But then, smash cut to the newly discovered quantum world of Heisenberg and Niels Bohr. Down at the atomic level, things are chaotic, they're governed by probability, and get this, they are completely dependent on the observer. An electron moving from point A to point B simply doesn't take a definite single path like a billiard ball rolling across a table.
Which brings us to our second chapter, Heisenberg's uncertainty.
Now, this is Heisenberg's uncertainty principle. It states that there's a fundamental impossibility of knowing both the exact position and the exact momentum, so the speed and direction of a quantum particle at the exact same time. And I want to be incredibly clear here because this trips people up. This is not because our microscopes are too weak or human technology is just flawed. No, this uncertainty is a hardwired law of nature itself. It is literally baked into the very fabric of the cosmos.
It actually operates exactly like a seesaw. If you set up an experiment to measure the position of an electron with super high accuracy, your accuracy for its momentum instantly drops. You completely lose track of where it's going. And conversely, if you measure its speed accurately, well, its exact position becomes a total blur. The particle simply refuses to possess both definite properties simultaneously. It's wild.
Mathematically, this relationship is expressed as delta x times delta p is greater than or equal to h, which is Planck's constant. Now, Planck's constant is an incredibly, unbelievably tiny number, which is exactly why we don't notice this uncertainty when we're, say, tossing a baseball or driving a car down the highway. But down at the microscopic level, this mathematical floor is where the familiar, predictable logic of reality completely breaks down and a totally new set of rules takes over.
All right, moving on to Chapter 3, the classical language paradox.
This brings us to a really frustrating trap that scientists fall into, and it's all about language. When physicists try to describe all this quantum weirdness, they just hit a brick wall. We're forced to use everyday, classical words to describe phenomena that are inherently unclassical. Look at the questions we usually ask. We ask, is the electron a wave? Or is the electron a particle? But the actual truth is, it's neither. It doesn't behave like a wave on the ocean, and it doesn't behave like a speck of dust. Yet we have absolutely no other words in our human vocabulary to describe it.
Heisenberg perfectly articulated this dilemma. He wrote, "The concepts of classical physics are just a refinement of the concepts of daily life and are an essential part of the language which forms the basis of all natural science." What he's essentially saying here is that we're trapped. We know these words are inadequate, we know they don't perfectly fit the quantum reality, but they are literally the only tools we have to communicate our experiments and our results to one another. We just can't abandon them.
Niels Bohr, who worked really closely with Heisenberg, used the principle of complementarity to explain this. He noted that asking if an electron is a wave or a particle is a fundamentally flawed question. It's kind of like pointing into empty space and asking if that specific point is above or below Australia. I mean, without the context of the Earth, without a specific point of reference, the words above and below just lose their meaning entirely, right? Similarly, wave and particle only have meaning based on the very specific experimental context we use to measure them.
Let's see how this builds as we move to Chapter 4, Probability and the Possible.
So if we can't definitively pin down an electron's path and we can't perfectly describe what it is, how do physicists even map out this reality? Well, they map out a universe built on chance rather than certainty. Heisenberg actually turned to an ancient philosophical idea to make sense of the math. He brought back the Aristotelian concept of potentia. You see, in the quantum world, before an electron is measured, it isn't fully real in the way you and I understand reality. Instead, it exists as a bundle of mathematical tendencies, a set of probabilities. It exists in this weird intermediate layer of reality, somewhere hovering between absolute nothingness and actual physical existence. It is pure potential.
And this completely destroys the image most of us were taught in grade school. You can just throw out that classical, misleading idea of an electron spinning in a fixed, definite track around a nucleus, like a tiny planet. The accurate reality is a probability wave. It's a mathematical cloud of statistical possibilities that only tells us the likelihood of where an electron might be if we actually decide to look for it.
Which brings us to the grand finale, Chapter 5, Observation Creates Reality.
Let's walk chronologically through exactly how a quantum event unfolds according to Heisenberg. Step 1, we start with the initial state, which is just a big set of possibilities. Step 2, these possibilities are represented by the probability function, that realm of potentia we just talked about. Then comes Step 3, the act of measurement. This is the crucial interaction with a measuring device, a physical piece of reality. And finally, Step 4, that act of measurement forces the entire system into an actual reality.
The very moment the observer interacts with the system, grasping into that glowing, undefined potential, that elusive cloud of statistical possibilities collapses. Reality literally snaps into existence the moment it interacts with our measuring devices. It's like a giant puzzle instantly assembling itself just because you glanced at it.
Physicists call this exact moment the quantum jump. It's the sudden, discontinuous transition from the possible to the actual. It is not a smooth evolution. It's a sudden, abrupt shift, where a mere tendency instantly becomes a concrete, physical fact just because we decided to measure it.
So the absolutely crucial point here is captured beautifully in this realization from the source text. It says, the word happens can only apply to the observation, not to the state of affairs between two observations. Think about what that means. According to the Copenhagen Interpretation, if you are not observing the system, the very concept of something physically happening is entirely meaningless. There is no hidden reality secretly taking place behind the curtain when we look away. The observation is the happening.
Which leaves us with a profound, lingering question to end on today. If the building blocks of the universe require the act of observation to transition from mere potential into actual existence, what does that make us? We aren't just passive spectators sitting in the audience of the cosmos. To the simple act of observation, we are active participants in literally creating the reality around us. Thank you so much for joining me for this explainer, and I will leave you to ponder that incredible thought. Hey everyone, welcome to this explainer. Today we're going to explore a truly mind-bending connection. We're looking at how the absolute weirdest, most counterintuitive discoveries of modern quantum physics were actually mapped out by ancient philosophers. Literally guys in togas, just sitting around and thinking roughly 2,500 years ago. It sounds totally impossible, right? But stick with me, because as we go through this, you'll see just how unbelievably far ahead of their time they really were.
So, did ancient Greek philosophers actually predict quantum mechanics? I know, it sounds like a totally crazy question. We normally think of modern physics as something born in massive particle accelerators with billions of dollars of high-tech equipment. But wait until we dive into how classical reality just completely breaks down at the atomic level, and how the ancients actually saw that exact breakdown coming centuries before the very first microscope was even invented.
To really wrap our heads around this, we're going to look at some brilliant insights from Werner Heisenberg's foundational book, Physics and Philosophy. Now, Heisenberg wasn't just a historian. He was literally one of the founding fathers of quantum mechanics. And in this text, he connects his own groundbreaking science straight back to ancient Greece. He realized that the philosophical crises modern physicists were facing, well, they were the exact same crises those early Greek thinkers faced when they tried to figure out what the universe is actually made of.
Okay, let's jump into Section 1, the quantum reality shock.
So, for a long time, thanks to thinkers like Isaac Newton, we kind of just assumed the universe was basically a giant predictable clockwork machine. But then, the quantum revolution happened, and it completely flipped the script. We really need to remember why this matters to you, right now. Get this, the table you're sitting at, the device you're watching this on, it's not actually solid matter. What you think is solid right there in front of you is actually just a mathematical probability of energy. At the subatomic level, the whole idea of a solid thing existing in a specific spot, it just completely vanishes. Poof. Check out this massive gap on the timeline. We start way back around 500 BC with the pre-Socratic philosophers, making these huge conceptual leaps about the nature of reality. Then, we skip to the 17th century where Newton and Descartes established that really rigid mechanical view of the world. And honestly, it took until the 1920s, with the Copenhagen Interpretation of quantum mechanics, for science to finally catch up to the Greeks. We basically had to wait until classical mechanics completely failed us at the atomic level.
The final nail in the coffin for that old classical physics was Heisenberg's uncertainty principle. The crucial point here is that you simply cannot know both the exact position and the exact momentum of a quantum particle at the same time. And this isn't just a glitch in our measuring tools, it's a fundamental property of nature. The crazy part? The very act of observation literally creates the reality. That means particles aren't definite things until we actually measure them. Until then, they exist only as probabilities. Wild, right?
Moving on to Section 2, Heraclitus and how fire is energy. Okay, so if matter isn't a solid thing, what exactly is it?
Let's travel back to ancient Ephesus and ask the philosopher Heraclitus. He argued that fire is the primary driving force of the universe and that absolutely everything is in a constant state of transformation. Well, guess what? Modern physics says essentially the exact same thing, just swapping terms to state that energy is the primary substance. Seriously, if you just swap that ancient word fire for energy, Heraclitus sounds exactly like a 20th century quantum physicist.
Let's look at how beautifully these concepts line up. Just like Heraclitus argued that everything is born from the conflict and transformation of fire, modern physics shows us that energy transforms into motion, heat, and light. It's the absolute fundamental cause of all change. Today, our massive particle accelerators actually prove that enormous kinetic energy physically creates the very elementary particles we observe out of nothing but energy itself. The conflict of energy literally gives birth to matter.
Up next, Section 3, Democritus versus modern atoms.
Let's see how all this builds on another ancient genius, Democritus, the guy who literally gave us the word atom, which means indivisible. He knew that to find the ultimate fundamental building block of the universe, you have to strip down reality step by step. Step 1. Democritus realized true atoms wouldn't have sensory traits, so he took away color, taste, and smell, leaving just geometric shapes moving in a void. Step 2. Modern physics takes it even further. We had to take away permanence and solid mass entirely, leaving nothing but abstract mathematical probability.
Now, here's where the ancient Greeks were slightly off, and it's a super fascinating distinction. Democritus believed his atoms were indestructible and eternal. Once a block of matter, always a block of matter. But thanks to the equivalence of mass and energy in modern physics, we now know elementary particles are not eternal, unbreakable building blocks. They're actually just transient manifestations of energy. They can be created in high-energy collisions and then completely destroyed, turning right back into energy.
And this brilliant shift really highlights our modern dilemma. A fundamental particle today doesn't even have the property of being in a specific place. It doesn't have an exact position, it doesn't have a specific trajectory, it's definitely not a solid little sphere. As Heisenberg himself noted, it's actually much closer to the old Aristotelian concept of potentia. It's just a tendency to exist, basically an abstract mathematical wave of probability vibrating in the quantum field.
All right, Section 4, Plato's mathematical universe. So this brings up a massive, massive question. If particles aren't physical, indestructible objects, what is actually holding the universe together at the fundamental level? I mean, if there's no stuff at the bottom of everything, what is there? This brings us to a mind-blowing realization that echoes the ancient mystics perfectly. The Pythagorean school famously declared, all things are numbers. They believed mathematics wasn't just some human tool to measure the universe, but that it was the literal foundation of reality itself.
Plato took this mathematical obsession to the next level in his dialogue, the Timaeus. He theorized that the elements weren't made of physical substance at all, but of purely mathematical, geometric shapes. Earth was a cube, fire was a tetrahedron. But here's the kicker. He argued these shapes could be broken down even further into underlying 2D triangles. He was essentially saying that if you look closely enough at matter, the physical substance completely dissolves into pure mathematics.
And this is exactly where we find ourselves today. When physicists smash particles and colliders, they don't get smaller physical pieces of a thing. They don't find a tiny hard core. Instead, they just get mathematical symmetries that describe energy fields. The fundamental laws of nature are just mathematical equations, and the particles, they're simply the solutions to those equations. Proving Plato was essentially right all along. The deeper you go, the physical world just vanishes, leaving only math.
Let's wrap it up with Section 5, Ancient Wisdom, Modern Science. So how do we tie this beautiful 2,500-year philosophical loop together in our explainer today? How do we reconcile the sheer genius of the ancients with the precision of modern physics? Well, it turns out that after spending billions of dollars on vast underground colliders and developing incredibly complex math, the deepest philosophical truths of quantum mechanics were already conceptualized by guys sitting in togas without a single microscope. They foresaw that science would have to shift away from physical things and move toward pure mathematical probability. They understood that reality is just a dynamic, ongoing transformation of energy. And perhaps most profoundly, they recognized that we aren't just spectators. The observer is an active participant in the universe. As you look at the world around you today, just remember that everything you touch, see, and interact with is fundamentally just energy and math. The solid world is kind of an illusion built by your senses. And that leaves us with a truly fascinating question to ponder.
If our absolute most cutting-edge science has led us right back to ancient philosophy, what ancient truth will we scientifically rediscover next? Think about that for a while. Thanks for joining me on this explainer, and until next time, keep questioning the reality around you.
Welcome to today's explainer. We are jumping straight into what is honestly probably the greatest philosophical mystery of modern physics. We're pulling all of this directly from Werner Heisenberg's incredibly foundational text, Physics and Philosophy. So buckle up, because we're going to explore a glitch in the matrix of classical science. It's a glitch that completely forces us to question the very nature of existence and how our own eyes might actually be shaping the universe.
I mean, just look around you right now. The everyday world feels pretty solid, doesn't it? A chair is a chair, a table is a table, whether you're actively staring at it or not. But what if I told you that at the absolute deepest, most microscopic level of reality, that simple rule just breaks down entirely? We're about to contrast our safe, predictable, everyday world with the downright bizarre quantum realm. It's a place where the simple act of looking at something might literally be creating reality as we know it.
Section 1. The Quantum Paradox, a crisis in physics. Okay, so to really understand this crisis, we have to look at this massive contradiction that popped up at the turn of the century. The basic building blocks of nature, things like electrons and light, seem to possess two completely conflicting identities at the exact same time. It's wild. On one hand, they act like particles. Think of them as localized, solid little bullets that leave super clear tracks in a cloud chamber. But then on the other hand, they act like waves. They spread out over space, they create these complex interference patterns, and they basically just exist as fuzzy probabilities. You can probably imagine how much this absolutely messed with the heads of early physicists. For centuries, right, the classical Newtonian view of this perfectly predictable, clockwork universe was totally supreme. In that world, everything had a definite place, a definite speed. But suddenly, matter and light were doing things that completely defied common sense. The very fabric of objective reality was literally slipping through their fingers. The universe, it turned out, wasn't a reliable clockwork machine anymore. It was more like a shapeshifter. Move into Section 2, wave or particle, the core investigation. This whole question literally kept scientists up at night. Heisenberg himself actually wrote about taking these long, agonizing late-night walks in a park in Copenhagen, having these endless, intense debates with Niels Bohr. He kept asking himself over and over, can nature really be this absurd? Can a fundamental piece of the universe really be a localized point and a spread-out field at the same time? In classical terms, it's just a straight-up logical impossibility. And, not everyone was willing to accept this quantum weirdness. Albert Einstein, very famously, completely rejected this loss of certainty. He came out and declared, God does not play dice. Einstein clung really tightly to what Heisenberg describes in the text as dogmatic realism. Basically, that's the belief that the material world must have an independent, definite existence, totally separate from whether we humans are observing it or not. To Einstein, an electron had to have a precise location and momentum at all times, no matter what. He just figured our instruments were too clumsy to see it.
Section 3. Complementarity, an elegant solution.
So, how do we resolve Einstein's issue? Well, Niels Bohr steps in with this absolutely brilliant realization. He figured out that the wave and the particle aren't actually competing for the truth. They are just different, mutually exclusive faces of the exact same reality. You absolutely need both descriptions if you want to fully understand the electron, but nature strictly forbids you from ever seeing both at the exact same time. They complement each other rather than contradict each other. And Bohr actually takes this a step further, which is fascinating. He argued that asking whether an electron is really a wave or particle when it's just sitting there unobserved is a totally meaningless question. Heisenberg's text gives a great analogy here. Trying to define the electron without a specific experimental setup is kind of like asking if a location is over Britain or under Australia without giving any sort of geographical context. You just can't do it. The answer depends 100% on how you are looking at it.
Which brings us to Section 4, the observer's choice, forcing reality.
Now, this is where it gets crazy, because this framework puts you, the observer, right in the driver's seat. The detective actively forces the quantum suspect to choose an identity. If you set up an experiment designed to measure a wave, boom, the electron behaves like a wave. If you set up an experiment to measure a particle, it behaves like a particle. By simply choosing the measurement, you are physically forcing the universe to collapse all its possibilities and make a firm decision.
let's actually walk through Heisenberg's famous thought experiment to see exactly how this works under the hood. It's called the gamma-ray microscope. Imagine you want to find the exact precise position of an electron. Step 1, you target it. Step 2, to actually see it, you have to bounce light off it. But to get a really precise location, you need a super short wavelength. So you hit it with a high-energy gamma ray. Well, a quantum of a gamma ray, to be precise. Step 3, that high-energy quantum hits the electron so violently that it permanently alters the electron's momentum. So you gain perfect knowledge of its position, but in doing so, you've completely destroyed your ability to know its speed. And this just brilliantly hits the nail on the head regarding the core truth of quantum mechanics. We cannot, under any circumstances, simply observe the atomic world passively. There's just no such thing as a detached observer. Our very act of measuring physically disrupts and literally creates the specific reality we're trying to measure. The observer and the observed are deeply, permanently tied together. Finally, Section 5, a new reality, the philosophical paradigm. So all of this builds up into what we call the Copenhagen Interpretation. And this interpretation just totally dismantles the classical idea of a clockwork universe. It flat out rejects Einstein's dogmatic realism. Instead, it says that before you look, an electron doesn't exist as a solid physical thing. Heisenberg actually borrows a concept from Aristotle here. He says it exists merely as a set of potentialities. It's just a ghostly cloud of statistical probabilities. It is only the physical act of observation that collapses those fuzzy probabilities into a single concrete reality. Bohr really summed up this profound wisdom beautifully. He realized that our everyday human language and our classical concepts of space and time, they just don't cut it in the quantum realm. And why is that? Because we cannot separate ourselves from the universe we're trying to figure out. In Bohr's own words, when it comes to the great drama of existence, we aren't just mere spectators sitting out in the audience. We are active actors, right there on the stage. Which leaves us with this final, honestly mind-bending thought to wrap up the explainer today. If the solid matter that makes up literally everything around us, our phones, our homes, our own physical bodies, is built out of these quantum particles whose reality is shaped by the very act of observation, what does that mean for the true nature of the reality you and I experience every single day? It is a huge question that physics is still grappling with, and it guarantees you're never going to look at the world the exact same way again. Hey everyone, and welcome to This Explainer. Today, we're going on a seriously mind-bending journey into the very fabric of reality. But, we aren't just going to be looking at atoms or equations. We're actually going to look at something much closer to home, the words coming right out of my mouth. We're going to explore the absolute limits of human language when it comes to describing the universe. And we'll be basing this on Werner Heisenberg's groundbreaking work, Physics and Philosophy. So get ready, because the way you think about reality is definitely about to be challenged. Okay, let's dive right into this. Imagine an electron. Is it a particle, like a tiny speck of dust? Or is it a wave, like a ripple on a pond? This impossible paradox is basically where our entire classical understanding of reality just shatters. And hey, if you've ever felt completely confused by quantum physics, you are in great company. The absolute greatest minds of the 20th century felt exactly the same way. Honestly, the confusion you feel is completely justified. In our normal classical world, things are predictable. Think of a billiard ball. You hit it, it rolls across the table, it has a definite position, a definite speed, and a totally predictable path. But contrast that with the quantum world. Down at the subatomic level, things look a lot more like an unpredictable probability cloud. The problem isn't just that the quantum world is weird. The real problem is that our everyday vocabulary was built to describe macroscopic objects, like those billiard balls, and it just wasn't made for this bizarre, fluctuating subatomic realm. Which brings us to our first main point, the shortcoming of everyday language. We're going to play the role of philosophical detectives here. Now, what's really interesting to think about is how quantum reality completely escapes our normal, clear-cut definitions. It's so abstract. When you try to hold a quantum particle in your mind using normal words, it just slips right through your fingers, kind of like trying to grab hold of pure light. It just doesn't work. Let's break down exactly why this happens. First off, human language evolved for survival, right? For hunting, gathering, building. Absolutely not for subatomic physics or the mind-bending scales of relativity. Take a super simple word like peace. You can have a piece of wood or a piece of iron, but you can't really have a piece of water. The word only makes sense in a very specific context. Applying our everyday words to the quantum realm is basically like trying to explain the difference between red and green to someone who is born colorblind. The concepts just don't translate. And when Heisenberg introduced his famous uncertainty principle, which basically said you can't simultaneously know a particle's exact position and its exact velocity, he essentially broke those very words. Position and velocity literally lose their traditional meaning without that classical context. Trying to use them at the quantum level is, well, it's like trying to use a hammer to fix a smartphone screen. It's just entirely the wrong tool for the job. Heisenberg totally realized this profound trap. He pointed out that the concepts of classical physics are really just a refinement of our daily lives. They're essential for science, sure, but they don't fit nature exactly. We're sort of trapped. We have to use our everyday classical language to talk about our experiments, but that language inevitably leads to massive contradictions when we apply it to the subatomic world. So how on earth did physicists get out of this trap? Well, that brings us to our next phase, the escape to the mathematical world. Physicists needed a hidden route to bypass those linguistic roadblocks. Let me walk you through the workflow these scientists came up with to build a bridge over this huge gap in human language. Step 1. The observer sets up an experiment using classical macroscopic tools, like a cloud chamber or a Geiger counter. Step 2. Instead of using clumsy words to describe what's happening, the physicist translates the whole setup into an abstract mathematical probability function. Then finally, step 3. They translate the results of that math back into a classical observation, a click on the counter or a physical mark on a photographic plate. So, the absolutely crucial point here is that physicists stopped studying definite things and started studying probabilities. Actually, they revived this fascinating old concept from Aristotle called potentia. At the quantum level, an electron isn't some hard physical reality sitting in a fixed spot. Instead, it exists as a potentia, an objective tendency, or just a possibility of an event occurring. It's this whole world of potential just waiting to be realized. And the math is really just a tool. It connects our observations statistically. We basically have to drop the illusion that we can visualize the quantum world directly. Math allows physicists to calculate the exact probability of, say, where an electron will hit a screen, without ever demanding that we paint a physical picture of what that electron actually looks like while it's flying through the air. Which leads us to Niels Bohr's complementarity principle. This is where we solve our philosophical mystery of how an electron can be both a wave and a particle. Bohr, who was actually Heisenberg's mentor, introduced this brilliant idea of complementarity. Let's lock this mental anchor in because it's huge. Complementarity states that quantum systems possess seemingly contradictory properties, like being a wave and a particle, but they aren't actually contradictions. They are just complementary faces of the exact same reality. And here's the real kicker. Which face is revealed depends entirely on how we choose to measure it. Nature isn't contradicting itself at all. We are just asking it different questions. And this brilliantly illustrates how it plays out in practice. If you set up an experiment specifically to measure a wave, well, nature's going to reveal its continuous, wave-like nature, but you will completely lose the particle's precise location. On the flip side, if you set up an experiment to find a particle, nature gives you a precise location, but you completely lose the wave behavior. The observer actually forces the electron to make a choice. It's just fundamentally impossible to see both faces at the exact same time. To make this even clearer, ask yourself, is a quantum object a wave or a particle? Honestly, that is as totally meaningless as asking, is it above Britain or below Australia? Without the specific context of a globe, an observer, and a reference point, the question literally has no meaning. A particle is only a particle when you actually measure it as one. So, what does this all mean for us? Let's move to our new understanding of reality and see how this creates a profound sense of awe about our place in the universe. Here is the absolute mind-bending takeaway from Heisenberg's analysis. First, that strict, objective, classical reality, the idea of a universe just clicking away like clockwork whether we're looking or not, that is totally lost at the atomic level. Second, the very act of observation actually creates the reality of the electron. Until you measure it, it's just that potentia we talked about. Third, and this is probably the most important one, physics no longer describes nature in itself. It describes our human interaction with nature. We're only studying nature as it's exposed to our specific human method of questioning. And finally, despite their severe limits, we literally cannot escape using our everyday concepts to communicate what we find. Grounding this whole philosophical journey back to its roots, Heisenberg's work was incredibly revolutionary.
It forced scientists to admit that the tools of the mind, our concepts, our words, are just as much a part of the scientific experiment as the actual physical instruments sitting in the lab. I want to leave you with a thought to chew on today. Think about everything we just covered regarding the limits of our human vocabulary. If the words we use literally determine the reality we can understand and interact with, what parts of the universe remain entirely invisible to us simply because we currently lack the language to even describe them? Really makes you think, doesn't it? Thank you so much for exploring this explainer with me today, and keep questioning the reality around you.